Hello everyone. Today we will talk about MobileNetSSDv2 introduction. As we know, CNN tends to add network width and depth to get richer feature. This brings complex network structure. Therefore, MobileNets designed by Andrew G. Howard comes out. Today we will talk about MobileNets from 7 parts listed on the left-hand side. Firstly, let's look about the dipswise separable convolution, which the MobileNet structure based on. It can be seen as a form of decomposition convolution, split the standard convolution into dipswise and pointwise convolution. The kernel is applied for each channel of the input feature map and then combined for output. This reduces the computation and model size. Let's say we have standard input feature F, filter K, output G as the size shown on the figure. The cost for CNN will be product of the bottom equation. But for the dipswise separable convolution, let's say the same input and output. One convolution kernel is applied for each input channel using dipswise convolution, and then do a simple 1 times 1 convolution. Total cost will be sum of these two costs shown at the bottom. As you can see, the compare cost ratio of standard and dipswise separable tells us the larger the number of kernels or the size, the more significant the cost and parameter reduction. Let's look at an example. Here, for the same input and filter shape, the parameters and parameters number hugely reduced for dipswise separable convolution shown on the bar graph. Now we can look at the entire structure. The left figure shows the structure of block in MobileNets. It can be seen as MobileNets at BN layer and ReLU layer of dipswise and pointwise convolution. The table right-hand side showing the whole structure in detail for MobileNets. In MobileNetSSDv2, before dipswise convolution, it processed a 1 times 1 convolution for rising dimension. After dimension reduction, nonlinear activation functions such as ReLU no more used. Shortcut connections are made if and only if the input-output dimensions are identical. So here are two structures, the left-hand side with shortcut and the right-hand side without. Now let's talk about ReLU 6. In order to make the ReLU function have a good numerical resolution, the activation range of ReLU function should be limited to 6. The activation function is linear as long as it's between 0 and 6 as the picture shows.
Now we are going to go through two key features of MobileNetSSDv2, and they are inverted residuals and linear bottleneck. So first, recap the concept of the ResNet. Here you can see that inside the ResNet, there is a skip connection connected the beginning and the end of the residual blocks. And if you look at the number of channels here, you can see that the ResNet have a wide, narrow, wide structure. And the MobileNetSSDv2 is kind of like a combination of depth-wise convolution and ResNet. Here you can see there are 3 layers inside the inverted residual blocks. The first is the expansion layer to increase the number of channels. The second layer is a 3x3 depth-wise convolution layer, and the last layer is a 1x1 projection layer that reduces the number of channels. So unlike the residual block, the inverted residual block have a narrow, wide, narrow structure. We are doing this because when we apply a convolution layer to filter the data, we want to do it on high dimensional data in order to extract enough useful information. So that's why we first use the expansion layer to uncompress the data. So comparing to the residual block, original residual block, the inverted residual block have fewer parameters thanks to the depth-wise convolution layer. And it also have better performance comparing to the original ResNet and the network without residual block. And the second feature is the linear bottleneck. So the activation function in ReLU is an essential part of the neural network. However, the linear activation function like ReLU can cause serious information loss when the input have very low dimension. So if you look at the inverted residual blocks here, you can see that we use the expansion layer to uncompress the data and filter the data. So in these 2 layers, in the first 2 layers, the data is in high dimension and it's okay to use ReLU. However, in the last layer, the projection layer, we compress data and decrease the number of channels. The other thing that if you use ReLU here, it will cause serious information loss. So the solution is instead of using linear activation function, we use a linear activation function here. So here we build the bottleneck by ourselves. Here you can see that after a projection layer, 1x1 projection layer, we use a linear activation function. And comparing to using ReLU 6 in bottleneck, a linear bottleneck have better performance as well.
After introducing the architectures of MobileNetSSDv2, we implement a demo to demonstrate our modules by using transfer learning on sign language digit datasets. Besides modifying the output layer from 1000 classes to 10 classes, we also freeze the first half of mode and only trains 10th to 16th button block, since the pre-trained model has already learned lots of edges and corners details in the first half of it. All we need to do is train the last half of mode to classify the image. It took us 20 minutes to train on GPU in order to get our desired result. You can see further details in our notebook.
So in order to show the effect of MobileNet2, we visualize the training process. Firstly, we use virtual maps to show the deep-wise convolution in one block. And also we show the image of different photo blocks in different stages. And after that, we use sensor maps and gradients in heat map to demonstrate the feature selection and classification of MobileNet2. And finally, we visualize the process of testing MobileNet2. We draw the accuracy and the loss curves of its training and validation. And at the same time, we use the confusion matrix to view the classification of 0 to 9 gestures. And from the results, all the images in the test data are correctly classified, and this proves that MobileNet2 has strong classification performance and while reducing large amount of parameters.